Okay, let's have a quick look here. So close those up for a sec. Take a look at what we did. Actually, let's do one quick example of what we did yesterday first. So let's go back here. Yeah, let's try this. Okay, let's do this using synthetic division. All right, what did we do? This is stuff we ended up with. Shortcut. Okay, we got to write the coefficients. Go ahead and make our bracket. And then the coefficients of the numerator have to go in order right here. Let's get rid of all headphones, all that stuff. Need help with combos. Okay, so coefficients go here. What are they?
2.
So click those things all the way close, everybody. So 2.
0.
0, good. How come 0?
Because there's a term between x cubed and x.
Okay, good. Right, so we need to leave a column for every power of x, and we start with x cubed. Well, that means we've got to have x squared, x, and the constant. There is no x squared term, right? So we have to have a 0 coefficient. So we add the 0, then we do -3 in the x column and 4 in the constant column, and there's our remainder box, right? Okay, Robert, what number is going to go out front? Not -1. I think I heard it. What's it going to be? 1. How come, Lauren? No, because it's the 0 of the denominator, right? We want the value of x. Thanks. That's going to make the bottom equal to, let's see, hang on. He's not here. We want the value that's going to make the bottom 0, right? Remember, synthetic division is really, it only works if you don't have any x squareds or x cubes, right? If the biggest power of x is x to the 1. And for us, we're not going to really deal with any situations where the 0 of the bottom is a fraction. You can. And like in calculus, I show everybody in calculus how to do that. It's not that big a deal. But it's a little extra complexity. So for this year, we're only going to deal with denominators of the form x plus or minus some number, right? So it's always going to be easy to find the zeros. X minus 1 equals, x minus 1 equals 0. When x equals 1, right? So 1 is the number that goes out front. Okay, now what? What do we do? But what do I have to do first?
No, you bring the first term straight down.
Okay, I got to drop the 2 down.
And then you will.
Then I multiply. 2 times 1 is
2.
plus 0.
2.
What goes there?
2.
Plus -3.
-1. -1. Remainder is
3. Okay, so our answer then, yeah, you got to be a little careful with this. What's our answer going to be?
2x to the second.
Good. Okay, we know that's x to the second. How come?
Because the next term, because 3x to the third is gone.
Right.
And the next term after that is x to the second.
So, good, okay. And if we work back from the right, we know this has to be the constant, right? This has to be the coefficient of x. X squared, x cubed, x to the 4th, if they were there, right? We're just going to work our way from the constant up to the polynomial tree, just higher powers of x each time, right? So we end up with 2x squared plus 2x minus 1 plus, what's my remainder? 3 over x minus 1. Yeah, that's it, right? Okay, no big deal. All right, so let's look, I want to show you something different then. So let's look at the remainder theorem, polynomial remainder theorem. This is really simple. This tells us everything we need to know right there. So if a polynomial f of x is divided by x minus k, right, synthetic division, then what this tells us is that magically the remainder is always going to be equal to the value of the function at k. So if I plug the number k into the function and figure out what the value of the function is, it's always going to equal the remainder when we divide f of x by x minus k, every time. So this is how we might represent that, right? If p of x is my polynomial, okay, and I divide that by x minus k, then I'm going to get two parts to this, right? I'm going to get the polynomial part, and in our last answer, what did that look like? Well, it was the part right there. Oops. Right? This is the polynomial part. It's the part that came from those coefficients, right? Plus, I got the remainder part. So we get the polynomial part, just a regular polynomial, plus whatever the remainder is divided by my original denominator. In this case, it's just x minus k. K is just some number, right? Okay, I want you to think about something. What would happen if I were to multiply both sides of this equation through by the quantity x minus k? Well, no, actually it wouldn't. So look what happens if I multiply both sides through by x minus k. On the left side of the equation, those are common factors. That's on the top and that's on the bottom, so they cancel, right? So all I get on the left side is just plain old p of x, right? The original numerator, right? What's on the other side? Well, if I distribute the x minus k factor to both of those terms, I'm going to get x minus k times q of x plus, when I distribute to this one, I'm going to get that cancellation again, right? So I end up with something like that. Okay, so when we divide, think where this came from. If we divide a polynomial by x minus k, then if this is my answer, some q of x, some polynomial answer plus a remainder term, then this always has to be true. The original polynomial that we divided by x minus k has to equal x minus k times the polynomial part of my quotient, but then I have to add to the end some remainder. That's easy to think of in terms of numbers. Take the example 25 divided by 4, right? There's going to be two parts of my answer. There's going to be a quotient part and there's going to be a remainder part, right? The quotient just tells me how many times does 4 divide evenly into 25? Well, 6 times, right? With what remainder? 1. So I have a quotient of 6 and a remainder of 1, right? So then doesn't that tell me that 25 must equal 4 times 6 plus 1, right? 4 times 6 doesn't get me all the way to 25. It gets me most of the way, but then I have to add an additional 1 because the 4 didn't go in evenly, right? So that's the same thing we just did over here with a polynomial, right? If x minus k doesn't go into p of x evenly, it's going to go in q of x times, but I have a little bit of a remainder, then that must mean that p of x equals x minus k times q of x plus that little bit extra that I needed, right? Let's look at a specific example. So what about this guy here? What if we have 3x squared minus 4x plus 7 divided by x minus 1. Now, we could do that one, but it's not. I mean, the answer we would get if we did synthetic division is we would get 3x minus 1 for the polynomial part with a remainder of 6, right? So the answer would be 3x minus 1 plus 6 over my original denominator. But that also means then that 3x squared minus 4x plus 7 must equal x minus 1 times 3x minus 1, but that's not quite all the way there. Then I need an additional 6 to get there because it didn't divide in evenly, right? Okay? So if we, let's look at an example here then of when we try to evaluate this by the remainder theorem. Right? It said that if we divide a function by x minus k, right? So if I divide 3x squared minus 4x plus 7, if I divide that by x minus 1, well, we already saw what we got when we did that. We got this, right? Our remainder was 6 when we did that. Okay. By the remainder theorem, what that's telling us then is that if I plug 1 into my function, I should get back that same answer. That's what the remainder theorem says, right? The remainder of this quotient is equal to what I get when I plug whatever's being subtracted from x, the value of k, when I plug that into the original function. So let's just show that that works. Okay, if I plug in 1, what am I going to get? On the left side, I'm going to get 3 times 1 squared is 3 minus 4 plus 7, right? What about the right side of the equation? If I plug in 1 for x, I get 1 minus 1 times 3 times 1 minus 1. Well, what's 1 minus 1? 0, right? So that means that factor right there, if that's 0, 0 times anything is 0. And so the only part that's left over then is just going to be that remainder part, right? So we end up with 6 equals 6, right? It worked. So that should work not just for a specific example then. That should work for every example. So if I did the same thing, if I want to evaluate this function at k, well, I know that on the other side, if I plug in k for x, I'm going to get a 0 times something, which is always 0. The only part that's going to be left is r, is the remainder, right? So it has to work every time. So what's the point of this? This is kind of the proof, but this works out to be so easy. Then we get a freebie way to evaluate functions. If we want to do something like this, what if we want to do something like that example right there? What if we want to evaluate this function at 4? Okay, well, we can evaluate it directly, and that works. They're just big numbers. If I want to evaluate this directly, I'm going to plug 4 in for x everywhere. Well, those are big numbers. 4 to the 4th, that's 4 squared squared, so 250, so it's 512, that first term. Those are big numbers you're dealing with. 4 squared, 16, minus 48, plus 20, minus 11. So that's going to give us 464 plus 20 minus 4, so 484 minus 11, is equal to 473. That's a lot of computation, pretty dense computation. It's hard to do that in your head, right? But there's an easier way to do this. We could use the remainder theorem instead, right? The remainder theorem says that if I want to evaluate this function at 4, that's got to be the exact same thing as the remainder I get when I divide the polynomial by x minus 4, right? Well, what would that look like? If I were going to do the quotient of 2x to the 4th minus 3x squared plus 5x minus 11, all divided by x minus 4, what would that look like synthetically? What goes where?
Coefficients.
So the coefficients would be 2, 0. Good. And what number goes out front? 4, right? And then now it's easy, right? These are much easier computations to make. Drop the 2 down, what goes there? 8. 32. 29. Now that's not hard. If you multiply something by 4, you just double and redouble, What's 29 double? What's it gonna be?
50.
58 doubled.
Another number 16.
116, yeah, there you go. 116, so if I add those, I get, and then times 4 is just double and redouble. What's 121 double?
242.
242 doubled,
484.
484.
Yeah.
So what's my answer?
483. 747.
Well, that's, what do you know? Right? But isn't that easier, right? So if we wanted, we didn't even have to write this out as a quotient, did we? All we really had to do, if I wanted to evaluate my original polynomial at 4, all I had to do was write the coefficients in my synthetic bracket, which is what I did, right? And the number that goes out front is just whatever the value of x I'm plugging in is, right? And then my answer is the remainder. See what I'm saying? Not a big deal, right? Okay, so 2 for the price of 1. That synthetic bracket works for doing synthetic division, or we can do what's called synthetic substitution, we might call it, where if I want to just plug in a value of x, I plug it in, and the value of the function at 4 is just going to be whatever's in the box. Okay? All right, so that's the new stuff for today. No big deal. What I want you to do now we're going to, let's see, you need a little dessert from lunch, so how about try and give you a chance to earn some dessert here. So let's look at a couple quick examples. What's the answer to this? What am I going to do here? This is just properties of exponents. X to the 8th. Good.
I told him that.
Right? How come? Because what's the rule?
Bottom one up. Move the lower one up or down.
Okay, so if I'm dividing like basis, though, I'm going to subtract exponents, right? And 12 minus 4 is just 8, right? Okay. So that's no big deal. How about something like this? Now this is a little different kind of problem because there are many correct answers, but you just have to give one correct answer. So if I want to write x to the 18th in the form x to the n to the m, what's one way to do that? X to the 6th to the 3rd.
I told him that.
That works, right? There's one way to do it. What's another way?
Next to the
9.
Yeah.
Okay? So there's a whole bunch we could do there. There's a whole bunch we could do. Any of them would be right. Okay? All right, so here's first issue here. So I want you to open up Chromebooks, go to SBAC, review, go to the second one, the one with today's date on it. Password is lowercase e. Go in and let me see, make sure I got the right. Yep, we're good. Okay, go in and do page 1 on properties of exponents.
Okay, like 1, 2, 3.
Just do page 1.
All of it.
Yep. And then stop after page 1. E.
Password.
Lowercase e is password. So this ought to be the first problem you're doing right there. Okay, and then stop. Don't do the second page. Oh, I'm sorry, Morgan. That's a bad throw. Alexis?
She was needed.
Give it to Chris.
Yeah. I don't want that one. I didn't want that one.
Uh-huh.
Great.
Lauren? Think fast, dude.
This one's open, broken.
What?
Yeah. Where? Here.
Wait, is this what my dessert is?
Mm-hmm.
I was like cookies out of it or something.
No.
Maybe some Snickers or Twix.
You had the X.
Jeremy?
Smart of the chiropractor.
Oh, you did them opposite.
Hey, oh yeah.
Yeah.
I'm smart of the chiropractor. I just want you to know that. She was the first one and I didn't.
Oh. Mm-hmm. Yep. Brittany. There you go. Good catch.
She did that.
Because.
Got it, oh yeah.
Got it?
Yep. How'd you do good? Simple math.
How'd you get it?
It's already written out.
How'd you get it?
I added them.
I didn't put the X on the bottom.
You did them legally?
Yeah.
Okay. I'm trusting you. Your word's good, I'm assuming.
I'm still helping out Kara. She's struggling a little. Here's one for effort, man. Gotta keep that for later. There it is.
Robert. Justin. No, don't be throwing those around. You don't get any more. You're going to get DQ'd from future treats if you throw them.
Yeah.
Okay, you got another 10 seconds. Finish up. Okay.